So I'm very happy to introduce our first speaker. It's a keynote from Professor Ruzhu Wang from the Shanghai Jiao Tong University. And Professor Wang has published a lot, 12 books and over 600 co-authored international journal papers. And his main research areas include heat pumps, like today, but a more general green building energy systems and energy water air nexus. Ruzhu is now editor-in-chief of the Journal of Energy, which is also very well known in the field with a very high impact factor and also site score. So Ruzhu will be presenting today on research results of water as a refrigerant, and we are very much looking forward to your presentation.
Thank you
Now
very
you
much,
can.
Colin. And it's my great pleasure to share our research work for the use of water as a refrigerant in heat pumps. I'm Ruzhu Wang from Shanghai Jiao Tong University. At first, I say something about the background because in China, especially for the industry sector, we consume total energy nearly about 67%, and in which nearly about 60% is heat. And the mostly for the industry heat, we need it from 80 degrees to 200 degrees centigrade. Originally before, we use coal boiler or oil boiler or natural gas boiler, and later with the electric boiler. So this is all the consideration for the shift from fossil fuels to the green electricity. So in this case, because we have carbon neutrality strategies. So in this case, now electric boiler, if we use green electricity, so it's good, but efficiency is limited. So in this case, if we really could use heat pump, in this case, you input 1 kilowatt hour electricity, you get additional 1 kilowatt or 5 kilowatt from low grade thermal energy, then upgrade. So if we take a look of the refrigerants, what is the base refrigerants? I think nearly for the 4 stages, and especially now for the first stage, especially for reducing global warming. So a lot of new refrigerants, but actually, if we consider for heat pump uses, the water is the best. So not only for zero ozone depletion potential or zero global warming or other impact to environment, but also for the super high COP value. This is if we consider for the temperature lift of heat pump, 40 degrees is a condensing temperature as the output of the heating. So this, what you could see when the temperature is over 100 degrees centigrade. The water is the best refrigerant for heat pump. So also it's good and also economy and also security also. But if we consider water, could be also consider water as a steam for the heating medium. So in this case, it's a beta carrier in many industrial processes, especially for brain, dyeing, and paper making, and electrification, and so on. So it's easy for temperature control and also could get a high flux and even temperature distribution, and heat temperature could be from 100 to 200 degrees centigrade. So if we see that to compare with normal water, high temperature water to compare with steam, steam is the best. So that's why industry they need the steams. So in this case, if we consider water as a refrigerant, usually we use a refrigerant inside and then in the heat pump. So from the low temperature side and then using water as a refrigerant to generate high temperature. But we could also consider using the water inside and in combination with absorption heat pumps to generate with a cascaded hybrid system to get a more high temperature output. But if we consider steam as a heating medium, actually we could using high temperature heat pump to get water heated, and then you get maybe flashy space steam or steam compressors to generate high pressure steam for the applications. So in this case, for this topic, normally we consider refrigerant and also heating medium. So now we say something about a water-based closed cycle high temperature heat pump. So if we look this and water as a refrigerant, so the left side is actually the heat source temperature. Right is the output temperature for demand side. So by using heat pump, normally, if we consider water as a refrigerant, mostly that it's in this area from 80 degrees to 120 at the heating source, and then we generate to 140 or even 200 degrees centigrade. And normally, water-based closed cycle heat pump using water as a refrigerant, it has a high COP value, and also for the Carnot efficiency also higher than normal one, and the mass heating capacity also larger. But it has the disadvantages. Maybe the volume heating capacity is lower because the steam vapor, larger specific volume. And also vapor completion ratio is also high. And also discharging temperature could be also high. So this is some disadvantage, but advantages is that high COP values, high efficiency. And in this case, now we have several options and to consider use of compressors. Normally, very small scale, we could using Rhodes compressors, but now most popular is screw compressors. And the screw compressors, normally the capacity could from 100 kilowatt to nearly 1 megawatt or 2 megawatt. So this kind of scale. And also it's a completion ratio could be as high, nearly close to about 10. But if we consider for the industry uses, maybe centrifugal compressor is the best, but normally single stage compression, the pressure ratio is very small. So we need multi stages if we consider to use centrifugal compressors. And with our experience to use screw compressors, if we consider heating source with the heat, if we consider 80 degrees, and so if we need a heat pump to got about 120 with about a 40 degree temperature lift, so vapor compression in this case, the pressure ratio is high, and this causes also the bigger consumption of compressors for the energy consumptions. So then we consider whether it's possible to get the peak of this away. This, in this case, we consider to use liquid water injection. And in this case, with 3 stages injections, we could get discharging temperature reduced to very close to the condensing temperature. So in this case, also we reduce a lot for the consumptions of the work for the vapor completion systems. So based upon this technology, so we did some research work for use the waste heat about 80 degrees. And so use the flash vapor in the flash tank, and it comes to the vapor compressor, and then compressed to high pressure, and normally to get a condensing temperature 120, 130, or 140 degrees. And then release condensing heat, and the condensed liquid come back and then expand it, and then comes here again to get with the heat heated, and then come to the flash tank. So this is the process that what we could use water as a medium, so to get absorbing heat from the waste heat sources, but we're using steam vapor compression, the compressor, and then this is condensation process. So in this case, we verify from 80 degrees evaporation temperature to 115 degrees, 120, for example. This is 40 degrees temperature lift, it gets the COP value 4.5. Even this is for the 50 degrees upgrade. This is a 3.5. So this just shows uses of steam vapor nearly for the high temperature heat pump. It's really with a high efficiency. The COP value is high, and also by the uses of the water injection, also we reduce the power actually consumed for the compressors. Now we say something about a steam generating high temperature heat pumps. Normally, such kind of heat pump could have three kind of thermodynamic ways. The first way is we could have a several stage cascaded system. For example, if we use three-stage cascaded system, you could create nearly the temperature lift for about 120 degrees, for example. So this is three stages, and at the last this stage we could use the vapor compression, for example. And also we could use a double-stage cascaded system to generate 80 degrees or 100 degrees. And then later we're using heat transformer, second type, lithium bromide absorption heat pump, and to get the temperature upgrade to about 120 or 130 degrees. So this is a hybrid system. But if we talking about that, we output heat. So we steer because the industry needs the steam vapor as a heat carrier. So in this case, the industry asked us, Professor Wang, we do not need the heat directly, we need the steam. So in this case, we could try to use a two-stage, for example, vapor compression system to get the water heated into the steam. And then by the steam compressor, you could compress to high pressure, and directly in this case, this is similar as a boiler to generate the steam, and then you get a steam supply for the industry. So in this case, we could, the options, closed cycle vapor compression system. And so in this case, we could using the normal refrigerant heat pump with a two-stage cascaded. In this case, you create a high temperature, but you get water heated and vaporized to generate high temperature steam. And even we could have three stages if you use water as a third stage. So we could generate high temperature from 170 to nearly 200 degrees centigrade. In this case, you could produce steam from the water vaporization. So this is a closed cycle system. But we could also use a closed cycle system with open cycle compression. That means we have two stages, for example, even from the ambient environment conditions, ambient air, for example, to have two-stage cascade to generate about 80 to 90 degrees. And this could be used to heat the water into this temperature, and then you get a flash vapor. And then using the steam vapor compressor to get the high pressure steam for the direct application for industries. So in this case, water comes here, and then it's heated in the flash tank, and also some water comes to the injection of the compressors. So in this case, we could get very, very high efficiency and high pressure steam for the applications. So this just shows what we have done in using the two-stage cascaded heat pump, and in this case to produce about 80 degrees to 90 degrees temperature, and then come to the flash tank. And then we take the moisture, actually steam, from the flash tank, and then come to the compressor. In this case, we could generate this steam vapor, and actually this steam vapor could be used directly for the industry. So what we have done for the ambient temperature, about 20 degrees centigrade, to create steam vapor at about 120 degrees, the COP value is about 1.8. If we wanted to create 150 degrees, the COP value is 1.6. So in this case, we started some real applications, but also we tried another options, because if we consider for the high temperature side, if the compressor is not a matrix, we could also consider for the low pressure, low temperature side using two-stage normal vapor compression systems to get about 85 or 100 degrees centigrade or something. And then third stage will use absorption heat pump, the second type absorption heat pump, just to release the absorption heat. In this case, we could make good uses of this kind of absorption system, because during this temperature range, actually this system is very reliable and also high efficient. So in this case, we could use centrifugal compilation systems and cascaded with larger scale absorption systems. So in the laboratory, we already made such kind of tests for the small scale using the waste heat and to be upgraded to more than 100 degrees and with the output from the absorption heat transformers. So not only limited to that, and we also consider the usage of waste heat. And waste heat, maybe we could use a single stage to generate high temperature, condensing temperature, and then to get the water vaporized to generate steam. Or we use two stages here, one stage is lower, and then you created the waste heat from 40 to 60 degrees, but we're using single stage heat pump to generate about 19 degrees, and then with the fresh vapor to get the water heated into the fresh and vaporize, and then come to the high temperature steam. This is a compressor, to steam compressor, in this case to generate 120 to 150 degrees. So that means if we use waste heat, we could get the more high efficient and also vapor compilation system. Maybe single stage will be suitable. And also, we could use absorption heat pump. If we have 80 degrees, for example, or 90 degrees waste heat. In this case, we use second type lithium bromide water absorption heat pump to generate the temperature about 120 degrees or even more. And then cascaded with a water vapor compilation system. In this case, to create about 180 degrees condensing temperature. So in this case, we could generate a high pressure steam. And what we found by this kind of usage of waste heat, the COP value, finally, from about 80 degrees to 180 degrees, so nearly about 100 or 110 degrees temperature lift. The COP value could be from 2.5 to 3 point. So now I show some applications. The first case is what we have done using cascaded air source heat pump to generate about 80 to 90 degrees hot water, and then come to the flash vapor, flash tank, in this case to get a flash vapor, and then come to the steam compressor. And then we get about 120 degrees steam, and it just used for liquid processing industry. So normally this we could create when the ambient temperature, air temperature is about 20 degrees. We take heat from the air source, but we generate 120 degrees. This is about nearly 100 degrees upgrade, but we get a COP value about 1.95. So this is really very, very suitable for this kind of industrial. And after 1 year uses, and then the industry asked us then to we jointly so establish a new company, try to make it promotions for the more applications of such kind of technologies. And also then we developed such kind of air source heat pump for steam generations. This is another example in electroplating. And usually they need about 80 to 85 degrees. But originally they're using gas boilers to generate steam and for the industrial process. But now we replaced with air source heat pump steam generations to get nearly about 120 degrees centigrade. And then used for the industrial process. And the total COP value is about 1.8. And also for the yearly operation, to compare with the gas boiler, we save the cost nearly about 50%. So these are some examples, and now we are considering for the future application, especially we are facing the problem for the larger scale, for the waste heat from industry, mostly from 80 degrees to 90 degrees. We could make the waste heat hot water, and by fraction vapor, and then in combination with vapor compressors, and especially centrifugal vapor compressors, in this case to get large quantity, maybe 10 megawatt or 20 megawatt scale for the industrial applications. If we have the waste heat at lower temperature, maybe 60 or 70 degrees centigrade, we could use second type absorption heat pump, and then comes to get flash vapors, and then come to the water vapor compressor, and to generate high steam, high pressure steam. The third, if we do not have waste heat, we could try to use cascaded vapor compression system and absorbing heat from the ambient air. In this case, we also could get the steam, low pressure steam, and if connected with water vapor compressors. So in this case, for the industrial applications, it's could be very, very easily adopted. But for this, the key issue is the large scale, high temperature compressors for water. So normally we need, especially for the condensing temperature from 120 to 160, or even to 200 degrees centigrade. And the compressors now, because mostly now we use screw compressors, is already available. And the centrifugal compressor also available, but I think there is still a long way for the bigger scale and the economical, this kind of a centrifugal compressors with multi-stage and for the lear uses. And at the moment, there are already in the industrial, MVR is very popular to use centrifugal water vapor compressions. So this is from company Pillar, actually, for 1 megawatt scale, and to take just for the vapor compression from low pressure to high pressure. And the Skyven is another example, even for more bigger scale. So these are all based upon that we have a heat sink to get flash vapor, and in this case could be compressed to the high pressure. And also some companies like Lotex actually, they did also these things. And in this case, with a source nearly 100 degrees, you get about 150 degrees centigrade. So in this case, all this just show the examples based upon original MVR now extended to high pressure steam generation. And now in China, I think the industry also paid a lot of attention, and just this year for the China refrigeration exhibition, already we had this kind of 4-stage actually centrifugal compressors. And because we consider inside we need the injector of water, in this case to make an increase of the performance. So now for the 2 stages, they use 60 degrees temperature lift, or 4 stages, nearly about 100 degrees temperature lift. And using this kind of centrifugal compressors, we already had some demonstration project to generate steam up to about 140 degrees centigrade. So another company, Media, they announced that they could support for about 200 degrees steam vapor using 2-stage Mac lever centrifugal vapor compression system. And so, but currently it's a actually small temperature lift for this. But now I think they are trying to organize a variety of series for this kind of vapor compression system using a centrifugal compressor. So that's all of my talk, and here I just show some references and for the leaders audience, and if you are interested, because some of my presentation already available, that you could lead some publications there. So I think this is some research experience using water as a refrigerant and also as a steam vapor carrier for heat transfer, for the heat transfer medium. So I think this is a great chance. I think now high temperature steam vapor compression is a very, very important topic. There are still a lot of work to do, and I hope that exchange of informations and experience is really very important. So that's all for my presentation. Thank you very much.
Thank you very much, Ruzhu, for this very interesting talk, and thank you very much for your time.